This will be for the con exercise, construct exponential models. On the first day of spring, an entire field of flowering trees blossoms. The population of locusts consuming these flowers rapidly increases as the trees blossom. The locust population gains 87% every 2.4 days and can be modeled by a function L, which depends on time t and days. Before the first day of spring, there were 1,100 locusts. Write a function that models the population t days since the first day of spring. All right, so these problems are going to be in the form of y equals a times b to the power of x. All right, and a is going to be the initial value. All right, it's basically the starting point or the starting number. So it says before the first day of spring, there were 1,100 locusts. All right, so we're going to start with y equals 1,100. That's going to be the initial value. And it's multiplied times b, and we're saying that the population gains 87% every 2.4 days. All right, so if you start with 100% of something and it gains or adds 87%, that's going to equal 187%. Okay, and in terms of a decimal, if you move the decimal over two places, that equals 1.87. So if you multiply the initial value, 1,100 times 1.87, it will add or make it gain 87%. So the value for B is going to be 1.87. Okay. Now, how frequently do we want it to gain 87%? Well, it says every 2.4 days. Okay. So if, and let me see, it says t is going to be the number of days. So if we just put a t here as the exponent, every time the day goes by, it's going to add 87% every time t increases by 1. But we don't want it to do it every 1 day. We want it to do it every 2.4 days. So you take t and you divide t, the exponent, by 2.4. Okay? This way, when t goes up by 2.4, when t is 2.4, the exponent's going to be 1. And then when t goes up by another 2.4, the exponent's going to be 2, and so on. So dividing it by 2.4 makes it increment by 2.4 days, right? If you have t equals 2.4, the exponent's going to be 1. And then when you have t equals another 2.4, which would be 4.8, the exponent's going to be 2, and so on. So this right here is your final answer. Okay, so it's going to be 1,100, and use the dot for multiplication, or you can use parentheses. It really doesn't matter. I'll use parentheses. Okay, and it's going to be 1.87. Okay, that makes it increases by 87% each time. All right, outside the parentheses, this is for the exponent, and this is for the fraction. So make it a fractional exponent, and we said it's going to be t over 2.4. Okay, because we want it every 2.4 days. So there's your answer. All right, Alexandra started studying how the number of branches on her trees grow over time. Every 1.5 years, the number of branches increase by an addition of 2/7 of the total number of branches. The number of branches can be modeled by the function n, depends on time t in years. When she began, her tree had 52 branches. Write a function that models the number of branches t years since she began studying her tree. Okay, so let's see. We're still using the same format, the same equation, okay, and that is just y equals a times b to the power of x. And we said a is the initial value. So when she began, her tree had 52 branches, so that's going to be your a. Okay, and every 1.5 years, the number of branches increases by an addition of 2/7. All right, so we know 100%. You start with 100% of something, and we know 100% equals 1. But we want it to increase by an addition of 2/7. So if we take 100% or 1 and add 2/7, we know that 1 is the same as 7/7. And if you add that to 2/7, that's going to equal 9/7. Okay, so if you multiply by 9/7, it makes it increase by 2/7. All right, so I take my initial value, 52, and I multiply that by 9/7. So this multiple makes it increase by 2/7 each time. Okay, now how often do we want that to occur? Well, let's see. If we use t, it said that t is the time in years. So if we put t as the exponent, it's going to do this increment every year. But that's not what we want. We want it every 1.5 years. So I have to take t and divide it by 1.5. Okay, this way when t is 1.5, the exponent's going to be 1. Then when t is 3, the exponent's going to be 2, and so on. So if it's 1.5, the exponent's just 1, and then add another 1.5, which is 3.0, the exponent's going to be 2, and so on. Every time it goes up by 1.5, the exponent increases by 1, and it multiplies this times the value. Okay, so that's your final answer right there. 52 times 9/7 to the t over 1.5. Okay, 52, parentheses, 9/7. Click outside the parentheses. Exponent button, fraction button, and I'm going to do t and hit the down arrow key, 1.5. So it's t over 1.5. All right, Tobias sent a chain letter to his friends, asking them to forward it. The number of people who received the email increases by a factor of 4 every 9.1 weeks. Function P, T is in weeks. Okay, initially it was 37 friends, write a function. Okay, so same format. Y equals A times B to the power of X. The initial value is A, that's 37. Okay, so we start with 37. And we want it to increase by a factor of 4. Remember, factor is the same as multiple. Okay, so increase by a multiple of 4. So obviously we're multiplying it by 4. And we want that to occur every 9.1 weeks. T is in weeks. Okay, so if I take the 4 and I put t as the exponent, and t is in weeks, it's going to get multiplied by 4 every week. But we want it every 9.1 weeks. So we take the t and we divide it by 9.1. This way, every time t goes up by 9.1, the exponent only increases by 1, and it gets multiplied by 4 an additional time. So this right here is the final answer. So you click in the box, you type 37, and you could use parentheses. I like that better. But if you want, you can use the dot for times to do times 4. And then click the exponent button and the fraction button. And the exponent is t over 9.1. So t, down arrow key, 9.1. All right, so there you go. If the 4 was a fraction, it's probably better to use parentheses, but either one works.